Hi, I'm Frank Nielsen, and today I would like to talk about the zeta distributions and their related distributions, which are power law distributions frequently met in application. We shall consider information measures between zeta distribution and also their information geometry as discrete exponential families. To start with, let us consider the diff distribution, which are discrete power law distributions with the following probability mass function, Psn. The normalization constants to make those distribution probability measures are called the generalized harmonic numbers, denoted by Hsn. The support of this distribution are the integers ranging from 1 to n. George Zeta was an American linguist who found that many empirical distributions of frequencies of words in human language text follow such power law distribution. Here I plot two Zeta distributions, one in blue with discrete support ranging from 1 to 5, and one in red with discrete support ranging from 1 to 8. The corresponding power parameters are denoted by the scalar S. For example, in this plot, we draw the log rank versus the log size for the 135 largest urban areas of the United States. In this log-log plot, we can see that the data are well fitted by a line on a range. This is explained by writing the log probability mass function and see that we get a linear equation in S, the power law parameter. Thus, the urban area size distributions follow a Zeta law. Here, we show yet another example of a log-log plot which shows the frequency distribution of US company sizes. Again, we see that the data is well approximated by a line in this log-log plot. Thus, we see that we can estimate the power law parameters by some line-fitting methods, but this is not recommended in theories as power laws exhibit heavy tails. In this third and last example, the authors have considered the 100 translations of the Holy Bible and reported in a table the fitted Zeta distribution parameters, which include the power exponent and the support n, which are the language vocabulary size used in the translation. For example, here we show the log-log plot of the translation of the Holy Bible in Esperanto and see that the word frequencies follow nicely a Zeta power law distribution. To analyze the specificities of various human languages and get an idea of their structure similarity or dissimilarities, we could use clustering techniques on their corresponding Zeta distributions. In general, clustering requires a notion of proper distances between their features, like here the Zeta distribution. Here we show a dendrogram obtained by hierarchical agglomerative clustering. Now that I have introduced Zeta distributions and their use cases, let me define the zeta distributions as limit of these distributions when the support is the full range of integers. In that case, the former normalized constants, which were generalized harmonic numbers, become the real Riemann zeta function. Because of the infinite summation, we now need the power exponent to be greater than 1. This contrasts with the Zeta distribution, which only requires the power exponent to be positive. On the plot here, I show the impact of the power exponent S on the probability mass functions of the zeta distributions. In practice, we need to calculate efficiently an approximation of the Riemann zeta function. There are many algorithms for fast numerical approximations, and the zeta function is often given as a primitive in many software packages, like the free symbolic computing software Maxima, which I use for my experiments. We can also lower and upper bound the zeta distribution as follows. Here I show the lower bound in red and the upper bound in blue on the zeta function. Notice that when parameter s tends to infinity, zeta s tends to 1. We shall now express the set of zeta distribution as a discrete exponential family. We can write the probability mass function of the zeta distribution as the following canonical expression of the densities of an exponential family. Thus, it comes as a natural parameter is theta equal s, and the minimal sufficient statistic is tx equal minus logarithm of x. The log normalizer, also called cumulant function or log partition function, is a logarithm of the zeta function. And since the Fisher information of an exponential family is the negative expectation of the log density, we get the following expression for the Fisher information of the zeta distribution using the first and second derivative of the zeta function. Here, for sanity check, we show the plot of the log zeta function, and we can check that it is a strictly convex function. Moreover, since the zeta distribution are exponential families, the log normalizer is always analytic. We should have a smooth function, which is strictly convex. A very interesting rewriting of the Fisher information can be done by using the so-called von Mangold function, which is often used in number theory. The von Mangold function of I is defined as log p if I equals p to the power of k for some prime number p and integer k, and 0 otherwise. The plot shows the von Mangold function for the first 100 integers. An interesting identity is to write the logarithm of any integer n as the sum of the von Mangold function for all dividers I of n. Because the set of zeta distributions form a discrete exponential family, this zeta distribution can be interpreted as maximum entropy distributions. Thus, if we ask to maximize the Shannon entropy of a distribution defined as a natural integer support with the constraint of the expectation of its sufficient statistic minus logarithm of x, we get the zeta distributions. We can now introduce the dual parameterization of exponential families, which are called the moment parameters or the mean parameters. The dual parameter eta can be obtained as a derivative of the logarithm of the zeta function. The maximum likelihood estimator for the zeta distribution coincides with the method of moments for the sufficient statistics. Therefore, we get that the MLE in the eta parameter is the average minus logarithm of the identically and independently distributed data. To get the corresponding natural parameter theta, we need to inverse the log zeta derivative, which is a complex task. In practice, several papers have studied different estimator strategies. The easiest approach is to do the line fitting in the log-log coordinate as we showed previously. This is called the quadratic distance estimator. It is shown efficient but suffers of the heavy tail property of the power law of zeta distributions. The Frechet-Darmois-Kramer-Rao lower bounds the variance of any unbiased estimator as the inverse of the Fisher information. Since the Fisher information of an identically and independently random vector is additive, we get that the Fisher information of an n-dimensional random vector is just n times the Fisher information of the zeta distribution. Thus, we obtain the following variance of the MLE expressed using the zeta and its first and second derivatives. Notice that this Kramer-Rao lower bound is tight only for exponential families. We thus easily recover a result that was published in this paper just by handling the zeta distribution as a discrete exponential family. We shall now compare the discrete power law with its continuous counterpart, which is called the Pareto distribution. The probability density function of a Pareto distribution, defined on the support, which is the interval 1 to infinity, is given as follows. Here, parameter S is called the shape parameter of the Pareto distribution. The set of Pareto distribution form a continuous exponential family with the following canonical decomposition. The Pareto distribution was introduced by Vilfredo Pareto, who was a sociologist. More generally, the Pareto distribution can be defined by two parameters, S and A, and its 2D Fisher-Rao information geometry has been characterized as a positive curvature manifold. In this synthetic table, I compare the discrete versus the continuous power laws. That is the zeta distribution on this column versus the Pareto distribution on the right column. Observe that the sufficient statistics is the same, but the range of the natural parameter is different. Also, the cumulative function of the Pareto has a simple expression as minus the logarithm of its natural parameter minus 1, but the cumulative function of the zeta distribution is expressed using the Riemann zeta function. Similarly, the Fisher information of the Pareto distribution as a simple expression, but the Fisher information for the zeta distribution is much more complex, as we have seen. Both distributions are maximum entropy distribution, but the Pareto distribution are obtained with respect to maximization of the differential entropy. We now come to define similarity coefficients and statistical distances between power law distributions. An important family of statistical divergences in information geometry are the alpha divergences, which can be expressed as a function of the Bhattacharya similarity coefficient, also called affinity coefficient. When the densities PS1 and PS2 belong to the same exponential family, the Bhattacharya coefficient can be expressed as the exponential of minus a Jensen divergence induced by the convex function taken as a log normalizer. Thus, we obtain a simple expression of the alpha divergences between two zeta distributions relying on the zeta function. For alpha equal 1/2, we get the square Hellinger divergence, which is the only symmetric alpha divergence. A property of the alpha divergences is that they tend to the forward Kullback-Leibler divergence or the reverse Kullback-Leibler divergence when alpha tends to 1 and -1 respectively. Thus, by choosing in practice some alpha values very close to this extreme case, plus or -1, we get an efficient way to approximate the Kullback-Leibler divergence between two zeta distributions. We can also use the property that the Kullback-Leibler divergence between two densities of an exponential family amounts to a reverse Bregman divergence for the log normalizer of the zeta distributions to express the Kullback-Leibler divergence between two zeta distributions. Furthermore, by using both the natural parameter and the dual moment parameter, we can express the Bregman divergence as a so-called Fechel-Young divergence. Therefore, we obtain the following expression of the KLD between two zeta distributions, where I use here the von Mangold function lambda. Let us now cluster a set of n text documents by their corresponding ZIF distribution, which are relaxed to zeta distribution. So all their support coincide to the natural integers. We can either use partition-based flat clustering, like the k-means or k-center clustering techniques, or some hierarchical clustering method. Since the densities are described by one parameter, S, and since the KLD between two zeta distributions amount to a Bregman divergence, the Kullback-Leibler divergence k-means amount to a 1D Bregman k-means clustering, and this can be solved exactly in 1D by using dynamic programming. This is because their Bregman-Voronoi diagrams have convex cells, and the clustering is called an interval clustering. If, on the other hand, we want to cluster a product of zeta distribution features, we will end up with a generic Bregman k-means clustering, and this problem is NP-hard when the dimension is greater than 1. Instead of relaxing the ZIF distribution to zeta distribution, we can also do k-means of ZIF distribution with different support, but with prototypes all being zeta distribution. In that scenario, we need to define a distance between the ZIF distribution and the zeta distribution, the prototypes. The ZIF distribution can be interpreted as a right truncation of the zeta distribution, and a formulae for the Kullback-Leibler divergence between two truncated densities of an exponential family with nested support has been recently reported as a duo Bregman divergence. Here we show the obtained formulae for the Kullback-Leibler divergence between the ZIF distribution and the zeta distribution. This figure visualizes the duo Bregman divergences induced by two strictly convex and smooth functions f1 and f2, with f1 dominating function f2. The equation of the duo Bregman divergence can be interpreted as a vertical gap shown in red here. The duo Bregman divergence is only a pseudo divergence when f1 is different than f2 because it cannot reach the value 0. When f1 equals f2, we recover the classic formulae of the Bregman divergence. Let me summarize our comparative study of discrete versus continuous power law distribution. I want to point out that the differential entropy of a Pareto distribution can potentially be negative, but the entropy of a zeta distribution is always positive. Also observe that the maximum likelihood estimator for the Pareto distribution admits a simple closed form formulae but this is not the case for the zeta distributions because we need to convert the moment parameter eta to the corresponding natural parameter, theta. To perform simulation and evaluate efficiency of various numerical schemes, we need to draw identically and independently variates of these continuous and discrete power laws. Here, I show some methods to sample a zeta distribution using the acceptance rejection method. This is taken from the book of De Broglie. And on the right side, I show how to sample a truncated Pareto distribution using the simple inverse transform technique. To conclude this talk, we have compared the zeta distribution with the Pareto power distribution from the viewpoint of discrete and continuous exponential families. We have seen advantages and inconveniences of both distributions from the viewpoint of computability. I would like to mention another recent related work which studies the discrete Gaussian distribution defined as maximum entropy discrete distribution on a lattice with first and second fixed row moments. Thank you very much for your attention.